Hi, everyone. My name is Yvonna, and I'm presenting on behalf of the Roche pRED Quantum Computing Task Force today. And so this talk is about our, let's say, quantum computing journey within Roche and hopefully help answer the question why we consider quantum computing to have the potential to be a disruptive technology. So for everyone who's not so familiar with Roche, here's the, let's say, overall structure of the group. So pRED stands for Pharma Research and Early Development, and we're one of the 3 independent R&D units within Roche. So when you see our use cases, that means that we tend to focus on early drug discovery. And so here is the core team members of this quantum computing task force. Oh, it's not showing up at all. Oh, okay. I'm not sure why that is. No. Oh, okay. Yeah, so that's the structure. And here is the task force member. Sorry about that. Yeah, so these are colleagues who has been working on the various different projects, and there are also other collaborators and colleagues, and their names will appear later as co-authors. So how did it start for us in this journey? We started back in 2018, more or less. This is around the time where we keep hearing the word quantum computing is going to be disruptive. So we just wanted to ask a simple question: can this technology really actually make a difference to the pharma industry, right? And so we went through first the exploration phase where we still have to bring ourselves up to speed on many of the topics. And as we can all appreciate, quantum computing is not a topic that's easy to grapple with mentally, right? And so one of the first steps that we made is to is to explore the landscape in terms of the different hardware providers. So we started by talking to the different teams, visiting their labs, and we want to understand what their strategy for scaling is, right? So we just list a couple of names in here, and we acknowledge that there are different modalities and exotic ones that could also still come up. And so we want to understand also what is the difference between this technology in terms of the different bottlenecks they can encounter, right? So be it to build sophisticated refrigerating systems to maintain coherence, or complicated control systems to also entangle qubits, right? So we want to understand a little bit what the differences are at a high level, not in the quantum physics level. And as the field emerges on a common set of metrics to compare these technologies, we also start to think in terms of qubit count and the error rate, coherence time, etc. And important part of that journey was also to be part of the ecosystem, right? So we went to many different conferences, and such as the one today, and to really tap into the community common source of wisdom, right? And we also started to collaborate with academic partners. Because we realized that we, without the background into, let's say, physics and theoretical computer science, we're not able to, let's say, really get behind the hype, right? So we sponsor master students and PhD students to work together on topics that are of common interest. And so the idea is that we want to have a scientific, objective view on the reality of quantum computing, right, in terms of its potential, but also its shortcomings. So it was also during this time that we started to converge on 3 different areas of interest, and we'll talk about it later. There's 3 different use cases. And it really should come as no surprise to anybody that those are the 3 use cases we focus on. Okay, so yeah, the next phase was expansion, right? So after spending 1 to 2 years educating ourselves, we really wanted to step up and actually make a difference in this field and start to actually bridge the gap between quantum computing as a, let's say, academic endeavor or as a technology, and to apply that to the pharma industry. So one of the ways that we did this is to be part of different consortia. So there's an example of the different groups that we're part of. So The QUIC and the quantum computing industry group are cross-industry consortia where we are actively contributing to establish representative use cases for pharma and to also provide ways to benchmark the ongoing development. So that's the improvement that happens in algorithm and hardware. So we want to be able to actually measure that in a quantifiable way. Right, and we also work with the Munich Valley to sponsor universities and to build up young talents in the field. And with Pistoia, this is a pharma industry specific consortia, and then we're aligning across the pharma industry about how we're all doing in this field. So without further ado, let's look into the next part of the presentation, which talks about our scientific use cases, right? So we wanted to focus on chemistry simulation, machine learning, and optimization, which are the three, let's say, champions of quantum computing that we keep hearing about. But we wanted to really tie this back to our day-to-day business. So with chemistry simulation, this means building models to accurately predict binding affinity, which has a strong then influence on how we do lead identification and lead optimization. For machine learning, we decided to look into image classification, but in general, as in many other different industries, the impact of machine learning is huge, right? And it spans across the whole value chain, from target assessment to the clinic. And also, we look into optimization, which also has the potential to impact the whole value chain. And we looked into protein folding. So given the time constraint and we have about 15 minutes before lunch, I don't really have, I guess, that much time to dive into details. So we'll just talk at a very high level about the first two use cases and with a little bit deeper dive on the machine learning use case. So the first one is chemistry simulation. So, okay, it's not synchronizing. There we go. During the early stage of drug discovery, we usually look at a huge library of molecules which can potentially bind to a specific, let's say, target protein. And in order to identify the most effective drug, which can bind with high specificity, we want to calculate the so-called binding energy between the protein and the ligand. If we don't do these calculations, we can also use high throughput, or in conjunction to making these calculations, we can also do high throughput screening, which are actually wet lab experiments to assess how well each molecule binds to the target, right? But these wet lab experiments are very work intensive, and it takes a lot of time and money to synthesize the compounds and actually perform the assays. So if we had a reliable way of calculating or even just ranking the ability for these molecules to bind to the target, then we can be much more selective with our lab experiments, right? And as people in this room can maybe appreciate this, to actually model this interaction is very complicated, the science, right? So the equations that model this behavior actually scales exponentially with respect to the number of electrons in the system. And so we actually would have to solve the Schrodinger's equation if we wanted to calculate exactly the electronic configurations. And it's classically, that's just kind of intractable at the moment if you go into larger systems. So here is also exactly where quantum computing has promised that it would be more efficient, because as Feynman said it, right? If you want to learn about quantum mechanical systems, you should study them using quantum mechanical systems and not classical systems. And so the task force was really interested to actually vet out this promise against reality, right? And we in the end chose to predict the binding affinity to the so-called base 1 enzyme, which has been identified to be part of the key pathway for certain diseases. And we have both public and in-house experimental data. So to validate any results, right? And so this is perfect for benchmarking. Now, to be honest, we don't really have time to go into the details of the method, but I'll just say for the experts in this room, we use something called DMET, so density matrix embedding method, to model the binding site, and we use VQE to get the ground state and the excited states. So now moving on to results, because we are interested in presenting the results. Where is it? Yeah, so this is what we actually presented to our chemists, and this is the most interesting thing for them, right? How do the quantum algorithm compare to ground truth? So as you can see, we actually did 2 sets of experiments, one on IBM and one on Honeywell machine. For both graphs, you can see on the x-axis that this is our, let's say, ground truth measurements as a proxy for the binding energy. So this is the results we got from our wet lab, and the y-axis actually shows the binding energy computed by the quantum computers. And so if you show this graph to me as a data scientist, I would say, hey, we got pretty good results. The R squared is 0.77, which means 77% accuracy, right? Not bad. But when we show these to our chemists, the reaction was more sobering. That the conclusion, I would say overall, is that these calculations are not good enough for practical use yet. So if you take a look closer, for example, between compound 67, which is a weak binder according to our experiments, and compound 69, a much stronger binder, the quantum computer is actually not able to distinguish between these two molecules. So that just went to show us, given the current setup, or using the current methods, we were not able to, let's say, start using them in our daily business yet. But I have to say, we have to keep in mind that these results were generated by simulating 4 atoms in the binding site. So if we're able to scale up and take into a larger area of interest, maybe the results would be different, right? So now, moving on to optimization. Making sure the slides sync. So we more specifically looked into how we can model the protein folding process in antibodies, since our biology is modulated by proteins. And actually how an antibody behaves and reacts to its environment, and also respond to different antigens, can be partly determined by the structure of this antibody in solution. So what does this mean for drug discovery? So if we are able to know with accuracy the 3D structure of these antibodies, then we can actually engineer better antibodies as a therapeutic methodology, right? So we can design antibodies that have better drug profiles, such as affinity, stability, so on. And for many antibodies, we know this, let's say, the recipe, how to create them. So this is something called the primary structure, the sequence of amino acids. But starting from this, let's say, recipe of creating them, it's still not easy to actually get the 3D shape out of them. Especially that the shape can be heavily influenced by the different conditions that they're under. And so classically, this means that there's a big trade-off between accuracy and speed. Because again, the equation which describe these interactions is very complicated, right, with many different terms. And so, again, similar to the other use case, we identified one specific data set that's interesting for us to compare the quantum algorithm against the best-in-class classical methods. This is the so-called H3 loop of the antibody. So this is actually the most challenging part to model in any antibody, because either in silico or to determine experimentally, because its shape can actually vary quite dynamically given small changes in the environment. But why it is important is because this loop is also most often the most important region in the antibody in terms of binding. So that's the reason why we chose the H3 loop. And again, without going into too many details, and if you're interested, please feel free to reach out to one of these co-authors on the project. And I will just then mention very briefly for the experts in this room that we chose to model the H3 loop using the charm family of potential energy functions, and we optimized the equation using quantum Monte Carlo method. Okay. And then, so here are the results, right? So instead of doing now hardware validation, we decided to do a theoretical resource estimation, because we're interested in seeing how this algorithm actually scales. And so you can see on the first row of this table that actually both quantum methods require much less, let's say, number of steps to execute compared to a classical method. But if you dive a little bit deeper into the algorithm, we actually did the math to work out the actual execution time. You can see that the quantum algorithm is actually significantly slower. And which was a little bit of a surprise to us. But the reason is really mainly due to the fact that the quantum Monte Carlo method is dominated by the Toffoli gate, which is orders of magnitude slower than the AND instruction on the CPU, right? So at least using this method, unless the clock speed of these Toffoli gates really increase dramatically, we don't expect to see a quantum advantage anytime soon for this use case. However, we still believe that this, let's say, benchmark use cases would be still useful to test out other algorithms, right? So we only tested out one specific algorithm. So if you want to benchmark other algorithms or to benchmark the improvement in hardware, then I think we should still do that using this use case. Now, last but not least, there's machine learning. Great that it shows up. So I hope, it probably doesn't need to be said anymore how machine learning has made a difference to all industries, right? And in specific, medical image classification, also segmentation and whole other tasks has been revolutionized by deep learning. So this is also, I would say, an area where quantum computing has a hard competition against, because we're competing against very efficient GPUs and very smart people working on classical methods. But we still wanted to take the challenge, right? And there are different ways you can formulate a, let's say, a quantum neural network. We chose to go the route of matrix multiplication, to model the artificial neural network as matrix multiplication, a series of them in the layer fashion, right? And this way we hope to leverage then the quantum computer's advantage in doing linear algebra operations, because there are so many mathematical proofs that show that some of these linear algebra can scale exponentially better on a quantum computer. And we actually also came up with Yvonna actually, who's also in the room with us, came up with two different architectures to do this, the so-called quantum-assisted neural network and also the orthogonal neural network. And the data set we chose is, again, open source. It's a downsampled medical images, which makes it ideal for testing NISQ-era quantum computers. And this data set also comes with the classical benchmark results, which saves us quite some work. And without going into too many details, I would also just like to show you briefly what it looks like, the solution. So we did our hardware experiment on the IBM machine, and then we implemented two different architecture, like I mentioned. So the first architecture really leverages NISQ-friendly subroutines to do this matrix multiplication or inner product estimation. And it has very nice properties when it comes to the circuit depth as well. There are many advantages, but one of them is, let's say, the resource requirement for circuit depth, and that's what makes them suitable for NISQ era machines, right? And then another one is orthogonal neural network. So classically, we also have let's say, research done to show that having orthogonal weight matrices in the classical case can already help improve accuracy and avoid the problem of vanishing gradients. But classically, this means it's very compute expensive to actually train in reality. So that's why we don't see so many practitioners use orthogonal neural network. But we were able to come up with an algorithm that effectively speed up this process quadratically. It's not logarithmic advantage, but quadratic, but we still consider that to be a promising result. And we tried out different architectures, right, for the two different, or let's say different network architectures for the two different ideas. And to show you guys the high-level results that we got. So this is the result that we got for the quantum-assisted neural network. So I know it's a lot to take in, but I would just say on the high level that our quantum algorithm gave us, let's say, similar level of accuracy to our classical algorithm, right? So that's the important, I guess, takeaway for us in terms of accuracy. And then you can see, so we did it on 2 different data sets, and for a more challenging data set called Retina data set, you could see the solution starts to look different when you go into higher dimensional input space. So you get better accuracy when you go to use 8 input size features versus 4. And I think the most important thing you can see as well is that there is a green dot lagging behind in terms of accuracy. This is when we both train and perform inference on the hardware. And unfortunately, this is also where we start to see the noise in the hardware kicks in, and then we see this drop in the accuracy. So that goes to show us that the hardware wasn't quite there yet, right? And we see very similar results using our quantum orthogonal network. Let me see if I can bring that up. No, where are we? Oh, that's a typo. Sorry, it should be the quantum orthogonal neural network. And so you can see very similar results here that if we are able to go into a higher input space, higher dimensional input space, we get more accurate results. And then again, you can see the effect of performing, let's say, these calculations on the hardware does have an impact on the on the accuracy. So that is about it in terms of the results. So just to do a little bit of advertisement for the work that we did is, if you want to learn more, there's the preprint, and here's members of the team who worked on this. And you can also, of course, come and talk to me if you have any questions, or Johannes. He's the expert, really. So to just conclude this, and not to be in the way between us and lunch, here are some high-level takeaways that we kind of got out of, or the task force took away from this journey, is that the benchmarks from our use cases really made it possible for us to really compare what the technology is at the moment against our own needs, and understand where we can focus our efforts further, right? So it was a really sobering exercise to do the deep dive into these use cases. And we also see that we still need to invest into fundamental research, right? So I don't think that that it's a closed deal, right? And we also see that collaboration between the industry and researchers, also hardware vendors in this space is vital, right? So we look forward to continue the collaboration, and I would say our stance is that we want to watch this space very closely, because we are still optimistic that hardware will be ready for commercialization. We're just not sure what that time span looks like at the moment. So thank you very much for listening, and if we have time, we can take questions. Yeah. Mm-hmm.
The thing I wondered a little bit is, I mean, we probably won't expect that they are like faster, but probably had a couple of problems where kind of the convergence or so of classical methods is so bad, yeah, like the sign problem issues or others, where kind of this timing thing is not as critical anymore. Do you see any use cases or so that are pointing more into the direction of using these methods for problems that have these very specific problems, so that Monte Carlo becomes more relevant?
So if I understand the question correctly, is if there are other use cases for Monte Carlo, is that, I would say yes, especially when you talk about physical simulation. I have to say though, within this task force, we chose this use case specifically because that's, let's say, the biologically most relevant use case. And being a small, let's say, task force, we don't work on this actually full time. It's kind of a part-time endeavor for us as well. So we have to be very selective. So we went for the biologically most relevant use case. Yeah. Yeah, I think that, thanks for the question. So I think it's in the same vein as the last question. We had to be selective, especially want to do hardware experiments. So we couldn't afford, I guess, to also maybe look at annealing, or also maybe this phase estimation we've heard during the conference is also a promising approach. It's just that I think we had to go with one approach, and VQE, at least what we heard back when we started the journey, is one of the more promising maybe venues, especially for this NISC era. Right. So I think, yeah, that was maybe the major decision factor for us is, are we able to implement it on the machine now? Right. So. Yeah.
That was a simple question. So I work for Bayer. We have a task force for quantum computing as well. So my question is the task force in Roche, is that a dedicated team for quantum computing only, or?
Right. Yeah. So like I think I said before, no, actually, most of us have a day job, so to speak. So I do image recognition or classification segmentation, 70% of my job. And then, we have people who have expertise in protein folding or this chemistry simulation. So we are kind of a mixed bag. Yeah. So, and we really did have to educate ourselves quite a bit and to bring us up to speed to understand really, even at a high level, what quantum computing is about. So yeah. Right. I think not very many, maybe I haven't heard that many companies being able to have like dedicated, maybe especially in pharma, right, to have a dedicated team. Yeah. Okay.
Thank you, Yvonna.
Thank you.
Good job.